let's investigate length and resistance. So we're going to build this circuit. We're going to have a battery connected in series to a bulb, a piece of nichrome wire, and an ammeter. So this is the apparatus we're going to use. There we have the bulb and the bulb holder, a 9-volt battery, and a battery clip, some crocodile clip wires, an ammeter, and then we're going to use this circuit board and this little screwdriver to help us to hold the elements in place. The nichrome wire is not yet shown here. So the first thing we do is that we screw the bulb into the bulb holder. Then we clip the battery clip onto the battery. We wind the positive end of the wire around one end of the bulb holder, and then we screw up one of the screws on the circuit board so that we can put the bulb holder in between the screw and the washer, and then screw down the screw again to make a firm connection between the screw and the washer so that the bulb holder is held nicely in place. And in so doing, the positive wire connected to the battery is also held nicely in place. Then we take the negative end of the battery holder. Now here I found that there was not enough bare wire to be able to make a nice connection. So I use a wire stripper to remove some of the insulation from the end of the wire. Then I screw up a screw to make a space between the screw and the washer. Place the bare wire of the negative side of the battery clip between the screw and the washer. Screw down the screw. So now I have the negative wire of the battery clip also held firmly in place. Now I take the red crocodile clip to indicate that it's on the positive side of the circuit, and I clip one end of it onto the bulb holder. Then I take the black wire, just to show that it's on the negative side of the circuit, and I clip it to the negative side of the battery holder. Now you can see I have a gap, and into that gap I'm going to place two things. One is the ammeter. You can see I'm connecting the negative probe of the ammeter via that crocodile clip, in effect, to the negative terminal of the battery. And then the positive terminal of the ammeter is going to connect to the second thing that I must put in this gap, which is the wire, the nichrome wire. So you can see now I have a gap into which I'm going to put the wires. So notice that the ammeter is in series because it is also in a gap. And you can see that there's another gap that is not yet filled, and into that gap I'm going to put one of the following wires. Either I'm going to put a 9 centimeter length nichrome single thickness wire, or a 6 centimeter or a 3 centimeter nichrome wire. So what I'm going to do when I collect the data is I'm going to connect each of these resistors in turn into the circuit, and then I'm going to see what the current strength is on the ammeter and how brightly the bulb shines. Of course, we will not get any reading if the ammeter is off, so we have to turn the dial of the ammeter, and we turn it until it says 200 M, and the M tells us that it's going to give us the reading in milliamperes. The 200 tells us that the maximum that it can read is 200 milliamperes. So if the current strength is any higher than 200 milliamperes, this setting won't be appropriate, and we would have to move it further to the setting that says 10, and then the reading would be in amperes. So can you see that this circuit diagram corresponds to what I've built? There's the battery. The battery has a battery clip to make the connection easier. The positive side of the battery is connected via the battery clip to one side of the bulb. The negative terminal of the battery is connected via the battery clip to the negative side of the ammeter. Then the positive side of the ammeter will eventually be connected to the nichrome wire. I just haven't done that yet. I haven't put the nichrome wire into the circuit yet. And on the nichrome wire's other side, it will be connected to the bulb. So in effect, I'm going to be building these 3 circuits because I've got 3 nichrome wires. A 3 centimeter one, a 6 centimeter one, and a 9 centimeter one. And I'm going to put them each in turn into the circuits. So you first need to predict in which case is the bulb going to shine the brightest? In which case is the ammeter going to give the highest reading? And why do you say so? Another thing we need to think about is what is our question we are trying to answer. To help us with this, answer this question. The variable we change directly between the 3 treatments. In this case, each circuit is a treatment. What is it that we make different between these three treatments, these three circuits? Is it resistor type, resistor length, or resistor thickness? And the thing that we make different between the treatments is called the independent variable. So what is the independent variable? It is resistor length. This has a short length, only 3 centimeters. This has a longer length, and this has the longest length of the 3. So they differ in resistor length. Because we make them to be different in resistor length, we think they will become different in another way too, and that is in resistance. So resistance is our what variable? Resistance is our dependent variable in this investigation. Remember, resistance is not the same as resistor. A resistor is a component which has resistance. Resistance is a property, meaning how difficult that component makes it for electric current to flow through it. So what is our focus question? How does, you must put the independent variable on that line, affect dependent variable? Pause until you've answered this yourself. How does resistor length affect resistance? Now, resistor length is easy to measure and describe. We've already done that. 3 centimeters, 6 centimeters, 9 centimeters. But we are not, in this particular investigation, going to actually measure resistance itself. We are going to deduce relative resistance by using indicators which tell us about resistance. We're going to use 2 indicators to tell us about resistance. Now, an indicator is something that shows us about something else. What are the 2 indicators that we are going to use in this investigation to tell us about resistance? We're going to use the brightness of the bulb and the reading of the ammeter. In other words, bulb brightness and current strength. Remember, an ammeter measures current strength. How are we going to interpret those readings? If we see that the bulb is brighter in one of the circuits than in another, what will that tell us about the wire's resistance in the brighter circuit? If we see a higher current strength in one circuit than the others, what will we deduce about the wire's resistance in that circuit? Answer these questions. Remember that resistance means how difficult it is for electric current to flow. Where it's easy for current to flow, is the resistance higher or lower? An easy situation has less resistance. A more difficult situation has more resistance. More current flows where the resistance is less. Less current flows where the resistance is more. Brighter and higher current strength means easy circuits. And how does that correspond to resistance? Brighter and stronger current both mean a lower resistance. So remember, our focus question is, how does resistor length affect resistance? But actually, we could just shorten that to how does length affect resistance? Because of course we mean resistor length. What else would it mean? What must be the same between our 3 treatments to make this a fair test? What are our controlled variables? Pause the movie while you write a list of all the important things that must be the same between these 3 circuits to make it fair. Be careful, because our independent and dependent variables must not be on your list. They must not be controlled. Because if you make the length the same between all 3, then how can we test the effect of length? So I hope this is the list you wrote. Notice, resistor length is not on the list because resistor length is our independent variable. The potential difference of the battery must be the same in all 3 cases. We must use the same resistance bulb. Well, I'm going to use the same bulb in each circuit. So in that way, of course, it will be the same resistance of bulb. The material of the resistor must be the same in each case. It's not fair if one of the resistors is gold and the other one is silver and the other one's steel or whatever. They all need to be made of the same material. And the thickness of the resistor must be the same in each. And I'm choosing a 9-volt battery in all cases, and the material of the resistor is going to be nichrome in all cases. So have you predicted in which case is the bulb going to shine the brightest? In which case is the ammeter going to read the highest current strength? And then what do those facts facts tell you about the resistance of the nichrome wire in each case? How does length affect resistance? Do you think that the shorter wire will have the most resistance? Or do you think that the longer wire will have the most resistance? And why do you say all of this? Pause the movie until you've discussed this with someone. Before we do the investigation itself, let us prepare a table so that we can put our data into it. Our question is, how does length affect resistance? So length is our independent variable and resistance is our dependent variable. So what do we write as the heading of our table? And also what do we write as the heading of the columns in our table? Table showing the relationship between length and resistance. Length is our independent variable and we are going to measure it directly. So we put it as the heading here in the first column. Its unit is centimeters, so we put that in brackets. But now you have to be a bit careful because in this particular investigation, we are not going to measure resistance directly. So you can't put resistance with its unit ohms as the heading of our second column. Instead of measuring the dependent variable directly, we are going to use indicators from which we're going to deduce the dependent variable. And what are those indicators? We've already discussed that. The current strength as given by the ammeter reading and the bulb brightness. So we're going to have two columns for the indicators of the dependent variable resistance. These two indicators are bulb brightness, which has no unit, and current strength. And we're going to use the unit milliamperes. So now we need to fill in the different lengths that we are going to use in our three different treatments. And they are 3 centimeters, 6 centimeters, 9 centimeters. Notice I don't rewrite centimeters because I have it in the heading already. So now we need to actually collect our data so that we can fill in these two columns. So we start with the 9 centimeter long nichrome wire, and when we connect it, the bulb doesn't even seem to be shining. If the room was darker and perhaps we could zoom in closer, we might see a tiny little bit of a glow. But the point is that the bulb is very dim. You can see that the current strength is fluctuating quite a lot, so it's rather difficult to decide what to write down as the current strength. I'm going to take 120 milliamperes as approximately the average of those values we've seen. Then we move our connection points to the 6 centimeter nichrome wire. Now we can see that the bulb is shining. It's not shining brightly, but at least it's visible that it is shining, so it's definitely brighter than it was just now. Again, the ammeter readings are fluctuating, but let's take the average there as about 150 milliamperes. We move our connection point to the shortest wire, the 3 centimeter. You can see clearly the bulb is a lot brighter. Again, we get fluctuation. Let's take the ammeter as around about 190 milliamperes. So here I've summarized our data inside our table as well as in the pictures below. What do we see? With the shortest length, we have the brightest bulb and the highest current strength. With the longest length, we have the dimmest bulb and the lowest current strength. Let's check if you got that yourself. Answer these questions to make sure that you understand what I've just said. Pause until you've done this. Circuit 1 has the shortest resistor. Its bulb shines the brightest and it's got the highest current strength. And from that we can see that it must have the lowest resistance of the 3 circuits. What about circuit 3? Answer these questions before you continue with the movie. Circuit 3 has the longest resistor length, its bulb is the dimmest, and it has the lowest current strength. And that tells us it has the highest resistance. So what is our conclusion? How does length affect resistance? Make sure you got it right. This first circuit, the bulb is brightest, the current is strongest. So what does that tell us about resistance? The resistance is less for this first circuit. That's why the bulb can shine so brightly and the current can flow so fast. But this last circuit, a long resistor, it's a dim bulb. It's a low current strength. That tells us the resistance is what? It's difficult. If it's difficult, that means the resistance is high. So how does length affect resistance? You can answer in this way. As is increased, on that first line must go the independent variable. Then the dependent variable what happens to it? Does it increase or decrease? As length is increased, resistance also increases, because the longer one, the 9 centimeter, had the highest resistance. How can we understand that using our analogies? First of all, let's think about it with a marble circuit. The first circuit with a short resistor is like having a short piece of sandpaper under the marbles at one area. This third circuit with a long resistor is like having a long piece of sandpaper under the marbles. Where is it more difficult for the marbles to move? It's more difficult when there's a longer piece of sandpaper. More difficult corresponds to more resistant. So there's more resistance where there's a longer resistor. And where it's more resistant, it's more difficult. The current flows slower, the bulb is dimmer. Where it's easier, where it's less resistant, the current is faster, the bulb is brighter. The longer the resistor, the more the resistance. You can also explain it in terms of water and pipes. So here we have a short, narrow pipe that the water must travel through, like the 3 centimeter, the short nichrome resistor. And here we have a long, narrow pipe that the water must flow through, similar to the long nichrome wire that the charge must flow through. The longer the difficult part, the more resistant it is. The more difficult it is, the slower the current will flow.